So in a bit more detail, with this close-up shot, you can see very nicely now the diaphragm moving. It looks like it's vibrating at a lower frequency, but that's because of the difference between the vibration frequency and the frame rate of the camera, potentially. But here you can see, I think quite clearly, the laser beam that's coming from the laser vibrometer, which is now out of shot. If I stop this vibration, you can hopefully also see the teardrop accelerometer, this tiny little accelerometer here, and you can see the laser triangulation sensor here, which has an infrared laser beam, an invisible laser beam, which is impacting or impinging on the top surface of the accelerometer. I'm currently vibrating this at 20 Hertz. We have 4 signals on here, the low frequency yellow signal showing the output signal to the amplifier in the speaker, the built-in amplifier. The green signal is displacement, the blue signal on channel 3 is velocity, which looks very nice and sinusoidal, and the red or magenta signal is the acceleration signal. First things to notice here are that displacement is quite lumpy, not a particularly good measurement. That could be genuinely because this displacement at this low frequency of this speaker is a little bit lumpy. Even though we provide it with a very nice sinusoidal signal, it's a mechanical system, so it doesn't move particularly nicely or sinusoidally. However, our velocity signal looks a lot cleaner, and the acceleration signal again looks quite smooth and sinusoidal, although you'll notice immediately that it's much lower amplitude. In fact, at this low frequency, displacement is relatively high amplitude, so the green signal is relatively high amplitude, the blue is lower amplitude, and the magenta signal is even lower amplitude. Generally speaking, for the reasons of amplitudes at different frequencies, acceleration is a better measurement to make at very high frequencies, and displacement is a better measurement to make at very low frequencies, because we get more signal and therefore our signal to noise ratio is higher. Velocity is a good measurement to make across the entire frequency range, particularly with respect to the frequency range associated with human hearing and human hand-arm vibration and body vibration, so from several hertz. Obviously the threshold of hearing is 20 kilohertz up to 20, I beg your pardon, lower frequency for human hearing is 20 hertz up to 20 kilohertz. So these are the typical frequency ranges that we're interested in when we're making measurements of machines. Sometimes we might extend to ultrasonics above 20 kilohertz. But across that entire frequency range, velocity is a good parameter to measure. Look what happens also between the phasing of these signals. So you'll see that there is a phase lag between the drive signal and the displacement signal, a slight phase. In fact, it leads slightly, the displacement measurement slightly leads the input signal. Importantly though, velocity is out of phase, as we know, by 90 degrees or pi by 2 radians, and similarly, acceleration is out of phase by a further pi by 2 radians. We know that because when we differentiate from displacement to velocity, we have a 90 degrees phase shift, and when we differentiate again from velocity to acceleration, we have another 90 degree phase shift. This becomes even more obvious or evident when I increase the frequency from 20 Hertz, and therefore my signal amplitudes change relative to one another. Look how, as we increase in frequency, the displacement amplitude becomes smaller, the acceleration amplitude becomes higher. We're now up to 75 Hertz, and these various signals are all of a similar amplitude with respect to one another, but we can very clearly see the phase differences, particularly if we align those traces together. Displacement and acceleration are potentially out of phase with respect to one another by 180 degrees. Even though it seems here that they're almost in phase, one of those signals has been inverted. The velocity signal, the blue trace, is definitely out of phase with respect to both of those two by something close to 90 degrees. The signal conditioning introduces a phase shift as well, so it's never absolutely clear that we have a 90 degree phase shift. It's a function of the signal conditioning, and it's also frequency dependent. So as we increase the frequencies further, these phase shifts might shift slightly with respect to one another. Once we get above 100 Hertz, we can increase the frequency very rapidly in 10 Hertz increments rather than 1 Hertz increments. And you can hear now the frequency at 250 Hertz, which is quite loud. Lots of acceleration, not very much displacement, approximately the same amount of vibration velocity. And as we increase, you can start to hear some other things resonating in the room around us. All the way up to 750 hertz. At 800 hertz, it sounds louder. We start to coincide with the resonance. And it becomes quite annoying at 850 hertz. And that's where I'll stop. I hope you found that video useful and interesting. Thank you.